Okay, we're going to continue looking at the energy subtopic of the managing resources topic, and we're going to look at the second part of that topic, and that is combustion reactions. Let's get into it. So the first thing that we need to really be able to do is write thermochemical equations. Writing thermochemical equations is a lot like writing balanced equations that we've done previously. We're just going to add a couple of steps to it. So let's take a typical complete combustion reaction. We take a hydrocarbon fuel, so that would contain hydrogens, carbons, and sometimes oxygens. I've got ethanol here, which also contains oxygen. We react it with oxygen gas, and in complete combustion, we will form carbon dioxide and water. Hopefully you've looked at those reactions previously. So let's look at a specific example here. We have ethanol, 2 carbons, alcohol functional group, plus oxygen, that'll go to carbon dioxide and water. It's always carbon dioxide and water are the products of any combustion reaction of a hydrocarbon. So the first thing we need to do is basically put in all the correct formula for whatever our fuel is: oxygen gas, which is O2, carbon dioxide, CO2, and water, H2O. Should be fairly straightforward. We then need to balance the equation, and half moles of O2 are okay. Normally we don't have halves in our stoichiometric numbers in front of things, but in this case we're allowed to have halves in front of oxygen, and I think the reason for that will become evident in a sec. So we go through balancing this equation. I would always balance carbon first, so we've got 2 carbons here, 2C, well, C here, so we need to put a 2 in front of that to balance that. Sorry, I've already balanced it. Then we would go to the hydrogens, 3 plus 2 plus 1, 6 hydrogens on this side. We'd come across here, we'd have H2, so we'd need 3 H2 to get 6 hydrogens. And then finally, we balance the oxygen, and this is when we can bring in the half. So now on this side, we would have 4 oxygens there, 2 2s, plus 3 1s there, so there'd be 7 oxygen. Now, obviously, O2, if you had 3 O2, that would be 6 oxygen. If you had 4 O2, that would be 8. We don't go and double everything like we might do in a normal equation. In a thermochemical equation, it's perfectly okay to put 3.5 in front of the O2. Remembering these represent moles. So this is saying 1 mole of ethanol, which is 6.02 times 10 to the 23 particles, or whatever Avogadro's number is. 1 mole of ethanol plus 3.5 moles of oxygen will go to 2 moles of carbon dioxide and 3 moles of water. So if you've done those two things, you're going to have 2 marks out of 4. Generally, if there's a thermochemical equation, it will be worth 4 marks. A normal equation will be worth 2 marks, and you'd be just doing the first 2 steps. The next you need to do is put in subscripts which show the state. So L for liquid, G for gas, S for solid, AQ for aqueous, which basically means dissolved in water. Hopefully you can remember that from last year. So ethanol is a liquid at room temperature, oxygen is a gas, carbon dioxide is a gas, and water is a liquid. So you've got to put those subscripts in. They're important in a thermochemical equation. And finally, you need to put in the enthalpy change for the reaction. So if you remember, we looked at these reaction profile diagrams here earlier in the year when we looked at rate of reaction. We have certain energy of the reactants here. Along this axis is like the reaction progression or reaction coordinate. Here we've got products. In this case, the reactants have more stored energy than the products. So when this reaction happens, that energy will be released in the form of heat. And that heat that is released is the enthalpy change. So this reaction here would be exothermic. Energy is being released. The products have less energy than the reactant, so energy is released. Exothermic, it would release heat, it would get hot. If it is exothermic, heat energy is released, we put a negative in front of the enthalpy change here. A negative, that shows heat's released. If there'd been an exothermic reaction and energy was absorbed, for example, like photosynthesis, where energy must be absorbed from sunlight, so that the products have more stored energy than the reactants, then that would be an endothermic reaction, and we would have a positive value for the enthalpy change for the reaction. So the way you show that in the reaction is you put delta H equals whatever the value of the heat energy released in that reaction is in kilojoules, and that is kilojoules per mole, because remember, this value here applies to this reaction here, and this was for 1 mole of ethanol. So that's 1370 or 1370 kilojoules per mole of enthalpy, per mole of ethanol. That is how much heat energy would get released. We'll do at least a demo, might get you a chance to do some practice on this as well, and hopefully that will also help your understanding of what this heat energy being released looks like, which is basically heating something up. And in the case when we do it in a prac, and when we're talking about it in a minute, we'll be using that to heat up water. The next thing we need to talk about also here is incomplete combustion. What you notice here is we have C3H8. This is propane. It's what comes through the gas taps in the lab, or is in your gas bottle for your barbecue at home. We can burn propane in an excess of oxygen. This is like the blue flame on your Bunsen burner. We can burn it in limited oxygen, but not too much, and we will get carbon monoxide release, which is a toxic gas. And if we close the air holes on your Bunsen burner, burn it with very limited oxygen, what you'll see is you get black soot forming over whatever you put in the flame. That soot can be a respiratory irritant also. All of these gases can contribute to greenhouses as well, the greenhouse effect, but you'll get this soot formed. If you look at those reactions, you can see here, if we do propane going to carbon dioxide and water, complete combustion, we balance that out, we need 5 oxygen. If we do propane going to carbon monoxide and water, we see we need 3.5 moles of oxygen. Here, if we have 1 mole of propane forming soot, we only need 2 moles of oxygen. So as the amount of oxygen available decreases, we get more and more incomplete combustion, and we get potentially these toxic gases formed. So what I've just done there is discuss the undesirable consequences of incomplete combustion, basically the formation of carbon monoxide, which is a toxic gas, or soot, which is a respiratory irritant. Again, hopefully that's a little bit of recap from what you've done in year 10 and or 11. There's one other thing that we need to explain here, which I've had to add in at the end, and that is explain why incomplete combustion is more likely with long chain carbon fuels than shorter chains. So when we think about short chain, we could think about things like methane with 1 carbon, ethane with 2, maybe even propane with 3 carbons. At the other end, if we get to things like hexane, heptane, octane that's found in petrol, where we have 6, 7, 8 and keep going with more and more carbon, we're more likely to get this incomplete combustion. And the reason that we're more likely to get incomplete combustion is, I can't read it underneath what comes up on my screen while I'm recording, but basically more oxygen is required per molecule of fuel. So if you're burning methane, for example, let me just quickly do this. If you're burning methane, I'm just going to write this up at the top. CH4 plus O2 goes to CO2 plus H2O because it's complete combustion. We would go here 1 carbon, 4 hydrogen, so we'd need 2 there. We'd need 1, 2 there, so we'd need 4 oxygen on side, so we'd see 2 there. So when we burn methane, we need just 2 oxygen molecules. When we burn propane, we'd need 5. And if we keep going up, we basically would say this pattern keeps going. So if you had, it doesn't matter, you need more and more oxygen. Now, the reason that you're going to get incomplete combustion is it's just harder to get enough oxygen in to a long chain carbon to convert it all to carbon dioxide. So as the molecule gets bigger, it needs more oxygen. You can't get enough oxygen present to the site of combustion, so there's a greater chance that you get incomplete combustion. I've actually never seen them ask that question in a test or an exam, but they could ask that question, so that's the explanation you'd need to give if you got that. Okay, let's keep moving. So over the next two slides, we're going to get into some of the maths, as in the MATHS maths. And I can hear some of you out there groaning, and I can hear the people who do physics and maths going, good, give me a language I understand. So how do we go about working out the enthalpy? And we're going to have a go at this in the lab, but and the good thing is now these equations are on your formula sheet, so you don't need to remember as many of these equations. Previously, these equations weren't on the sheet, and you did need to remember. So I'm going to just talk you through a little bit of the theory, and then in the next slide I'm going to go through an example calculation which will simulate what we will do in the lab, or at least as a demo during lesson. So we need to learn some terminology first. Firstly, Q. Q is what we use for the heat energy released in a reaction. So that's either in joules or kilojoules. So the amount of heat released is in joules. Later on, I'm going to also talk about, and I've already talked about, enthalpy being the heat energy released. Well, enthalpy is the heat released per mole. So delta H, if you like, is a special Q. It's what Q is equal to when you have exactly 1 mole of fuel. Delta T is the change in temperature. We are going to be using these fuels, and the way we're going to work out how much energy is in these fuels is we're going to use them to heat up water. And basically, the more they heat up water, then the more energy that's released. So the way that we work out how much they've heated up the water is by measuring the change in temperature of the water. MH2O is the mass of water that we are going to heat, as opposed to M, which is just the mass of fuel that we're going to burn. So we're going to burn a certain amount of fuel and use that to heat a certain amount of water. So MH2O refers to the mass of water we're heating. M refers to the mass of fuel that we're burning. C is the heat capacity of water. This is a really important value for us to work out how much energy is released. The heat capacity of water refers to the energy required to heat 1 gram of water by 1 degree Celsius. So if you have 1 gram of water and you want to heat it by 1 degree, you need 4.18 joules per gram per degree Celsius. So, you need 4.18 joules of energy, and that will heat the 1 gram, so that's per gram per degree Celsius. Per gram per degree Celsius. This value also has another name, and that is known as a calorie. 1 calorie is the amount, it's sort of like the old unit, it's like the inches and the feet type unit. 1 calorie is the amount of energy that it takes to heat 1 gram of water by 1 degree. So we can measure energy sometimes in calories, because we often worked out how much energy was being released by how much it heated up water. But the SI unit, the standard unit, is joules. So 1 calorie is equal to 4.18 joules. So you've probably heard people talk about calories in food. For those of you who have done nutrition, or you may have even done these experiments in earlier years, you might have burnt chips or nuts and that sort of thing, and use them to heat water up and use that to work out how much energy was stored in the fuel, in the food. N is the number of moles of fuel. M is the molar mass of the fuel. Obviously, we can work out the number of moles of the fuel by going mass divided by molar mass. And this, the rho, I think it's a Greek alphabet, but it looks a bit like a funny P, is the density of the fuel in grams per litre. And I'll show why you need to know that as well shortly. So there's 3 common units that we use to describe the energy of a fuel. The enthalpy change, which is the energy released per mole. So it's the energy you'd get from burning 1 mole of fuel. There's the energy density, and that's the energy released from burning 1 litre of fuel. Now, obviously, you're not always going to be 1 mole equals 1 litre. In fact, you're probably never going to have 1 mole equals 1 litre. So energy density is the energy released per litre, and the specific energy is the energy released per gram of fuel burnt. So this is how much energy per gram, how much energy per litre, how much energy per mole. Now, this formula is given on the formula sheet, both these formulas. The relationship between these two, is that the heat released, the way we work out the heat released is we times the mass of water by the heat capacity of water, that's the 4.18 value here, times by the temperature change. And that will give us the energy that is being released. Now, usually we will convert that energy into kilojoules. So 1 kilojoule equals 1,000 joules. So if you work this out in joules, then you need to divide by 1,000 to convert it into kilojoules. Then once we have the heat release, we can work out the enthalpy, and that is equal to, so the enthalpy delta H is equal to the heat release divided by the number of moles, and we can work out, as I said before, the number of moles by mass divided by molar mass. Now, I'm going to go through this in the next slide. So if you're feeling a little bit lost at the moment, that's okay. But I just want to explain all the background, and then we'll do an example problem next. Just couldn't fit them all on the same slide. You also need to be able to convert between energy density, i.e. kilojoules per litre, enthalpy, kilojoules per mole, and specific energy, kilojoules per gram. And the way that we do that, well, let's just go, this is probably the easiest one to think about first. If we want to go from specific energy to enthalpy, we want to go from kilojoules per gram to kilojoules per mole. Well, what we really want to do is we want to go from grams on the bottom to moles on the bottom. How do we go from grams to moles? Well, we use this N equals M on little m on big M formula. And basically, if we want to get moles, we've got to divide by the molar mass. But the molar mass in this case is on the bottom. So dividing by something on the bottom is the same as multiplying by something. So we've got to basically multiply by the molar mass. This can get a bit confusing. If we want to go the opposite way, then we've got to divide by the molar mass. If you get confused, I like to go to the units. If we have something in kilojoules per mole and we divide by the molar mass, and remember molar mass is how many grams per mole, so the molar mass of carbon is 12.011, that means 12.01011 grams for every mole of carbon. So if we divide kilojoules per mole, which is enthalpy, by molar mass, do the mass there, dividing by a fraction, so you times by the reciprocal, so grams per mole, instead of dividing by grams per mole, we times by moles per gram. The moles cancel out, we get kilojoules per gram there. So that just is my little check. If I want to go from enthalpy to specific energy, I've got to divide by the molar mass. And if I want to go the opposite way, I times. Now, I could do a similar process to show you how we go from specific energy to energy density and from energy density to enthalpy. In this case here, we need to times by the density. To go this way, we divide by. To go this way, we've got to times by the molar mass and divide by the density. Here, we've got to times by the molar mass, times by the density and divide by the molar mass. They don't come up that much, those unit conversions. I think it's easiest just to think your way through them if you get them. So I use this process here to check, and I often do it by trial and error. I won't try and model that right here, but I'm happy to go through some of those in class if we need to. So at the moment I'm suspecting, oh wow, there's a whole lot of things there and a whole lot of formulas and I've just got no idea what's happening. Let's have a look at an example, and I think you'll hopefully see it's maybe not as confusing as it seems once you get into it. Okay, so this data here is actually data from an experiment I ran in the lab last year. I will run an experiment too for you guys, at least a demo, if not an experiment, and we'll probably get similar data. But I think it's still, we can still just go through this data, and it's, it's basically a completely valid way to look at it. But I said after we've done it as a prac, it might make a little bit more sense. So based on the data in the table below, calculate the enthalpy of combustion of ethanol. So what we had in this prac was we had 100 grams of water. That was what we heated up. The initial temperature of that water was 24.5 degrees. The final temperature of that water was 45.0 degrees. So the change in temperature was 20.5. We heated that water up by 20.5. Now we had the ethanol in a little spirit burner. I'll show you what a spirit burner is if you don't know what one is in lesson. But initially we weighed that spirit burner and it had a mass of 198.65 grams. Then after we had heated up this water, we weighed it again and it had a mass of 198.00 grams. So we had used, and there's a mistake there in the notes, we had used 0.65 grams of fuel. That was how much ethanol it took to heat that water by 20.5 degrees. So the first thing we need to do is work out, well, how much heat was released in heating the water by 20.5 degrees. So we go the mass of water times by the heat capacity, that's the 4.18. That value is on your formula sheet along with this equation, times by the temperature change, 20.5 here, 8,569 kilojoules, which equals 8.57 kilojoules. Just going to go to three significant figures here because three significant figures was all I had in the mass of water and the temperature change. So that was the energy that was released in kilojoules. We just divided by 1,000 to go from joules to kilojoules. Then nextly, we need to work out the number of moles of ethanol that was burnt. So the molar mass of ethanol is 46.07. Work that out with either periodic table is probably the best. So we've got 2 carbon, which is just, if I do it very roughly, it's 2 carbon, that's 24. 1 oxygen is 16, so that's 40. And there's 6 hydrogens to get you 46. So number of moles equals mass over molar mass, 0.65 over 46.07 equals 0.0141 moles. That was how many moles of fuel, of ethanol, we burnt in that 0.65 grams. So now we can use this formula here that's on our formula sheet. The enthalpy change is equal to the heat released divided by the number of moles. So if we'd burnt 1 mole of fuel, that number there would be 1, and we'd say, oh, the heat released is the same as the enthalpy. 8.57 divided 1 is 8.57. But we had a lot less than 1 mole, so this number here is much smaller than 1. So when we go through that, we get a value of 608 kilojoules per mole. So in this reaction, we've calculated the heat energy released from burning 1 mole of ethanol would be 608 kilojoules. We only got 8.57 kilojoules released, but we only burnt a fraction of a mole. So that's the process for working out the enthalpy change. Next, calculate the specific energy of ethanol in this experiment. So the specific energy is the kilojoules per gram. We go, how do we convert that? We're going to divide by the molar mass. Now let's just say you couldn't remember, like I wouldn't probably be able to remember, that you have to do kilojoules per mole, to go from kilojoules per mole to specific energy, which is kilojoules per gram, you got to divide by molar mass. So let's say you went, oh, I can't remember exactly how to do this. So is it, hang on, that's a bit messy. Let's start again. Is it kilojoules per mole? That's what we have. Oh, do I go to times by the molar mass or divide? Oh, I can't remember. I think it's times. So if we times by the molar mass is measured in grams per mole. So if we times, then we are going to get, kilojoules grams per mole squared. Well, that's not kilojoules per gram, is it? So that must be wrong. So we'd go, no, that's not right. Put a cross through that. So let's go, what about if we divide by grams per mole. We divide by the molar mass. Or that means we go to times by the reciprocal. So, sorry, it's a bit messy. Times by moles over gram. Oh, the moles cancel, kilojoules per gram. We have the unit that we want. So, if you're like me and don't have a great memory, that's a way you can work your way through that conversion. So, divide by the molar mass, 608 divide 46.07 equals 13.2 kilojoules per gram. So we would get 13.2 kilojoules of energy from every gram of methanol we burn. Calculate the energy density of ethanol. Same thing, I won't go through this working out process, but if you look at the previous slide, you go to times by the density to go to kilojoules per litre. 13.2 times 789. This density needs to be in grams per litre. This is really important, grams per litre. And we would see there we would get 10,400 kilojoules per litre. So when we burnt ethanol, 10,400 kilojoules per litre. Now, the other classic question you get on this experiment is the systematic error question. So the true value for the enthalpy of combustion is, this is for ethanol, is 1,307 kilojoules per mole. Suggests why the value obtained was lower. Well, it would be lower because you had systematic errors, and those systematic errors would have been heat loss to the surrounds. When I do this prac, you'll see not all the heat will get transferred to the water. Some of it will heat up the container that the water's in. Some of it will be lost to the surroundings. The other thing you might notice is that you get some soot form in this experiment. That soot forming is indicating incomplete combustion. Incomplete combustion, which releases soot, will not release as much energy as complete combustion, which releases carbon dioxide and water. So that would be another source of systematic error, which is why you wouldn't get the true value. So, hopefully, if you watch that, then when we run through it in the prac, you'll see, oh, what he's doing in class makes sense, even if you're a bit confused now. If I've already done it in class before you watch this, hopefully this will be a good little bit of revision, and you'll be able to picture in your head that burning of the fuel with a spirit burner and a calorimeter, which is basically just a fancy beaker, and visualize what's happening there in terms of determining the enthalpy of combustion or the heat released from burning a fuel. Thank you.